I'm starting right now. This is a subject on pilot plants and scale-up studies. My name is Dr. Gary Tatterson. I'm with the Department of Chemical Engineering, or actually Chemical Engineering Program, North Carolina A&T State University. My contact number, if you really want to get in contact with me, is gbt@ncat. This is a very old phone number. Actually, it's still my phone number, actually. I'm going to run the course like this with the side notes over here as they come up. And usually this is a short course that's presented in front of people, an audience, but in this case it's being recorded, so there is no live audience. Please feel free to contact me at my email address or my telephone number if you have any questions. The course is based upon four of my books. These are all available on Amazon.com. They're very inexpensive. First book is a general literature search type book. Second book came out, Scale-up and Design of Industrial Mixing Processes. And from there I went to use the techniques in general with other areas. And the final book I start working on, or giving the solutions to problems that were in this book. I recognize reviewing this book that maybe my solutions weren't clear, so this time I included very clear solutions in here, as well as I had a number of articles and columns that I had wrote that's accumulated in this book. The course is divided into three areas. The why do you do scale up, and perhaps you could call management considerations, methods for scale up, systematic approach for scale up, and scale up traps and overcoming these traps. This material is directed towards understanding scale up in general. These are more specific scale up discussions about what occurs in an agitated tank. And this is about scale up research and pitfalls that one encounters. Anyway, up here I also talk about pitfalls, overcoming various traps. So let's dive into this, this material. The why, okay. The purpose of scale up is the creation of wealth. I mean, that's the primary objective. Examples of scale up is penicillin, TiO2, NutraSweet, flu vaccines, and I toss in the airplane just for some mechanical device scale up. Airplane obviously started out with one person aboard, and now they can put 500 people on an airplane, and in a sense that represents a scale up. Scale up depends a lot on trial and error, a lot on serendipity, and a lot on just simple luck. Luck visits those with a prepared mind. That's a statement attributed to Einstein. It's very, very true. The reason why you have a prepared mind, it's much like a football team or a sports team practicing. You get prepared for when the big game happens. It's the same sort of thing. You continually learn, you continually develop, and you're more likely to capitalize on luck. Let's take a look at the Wright brothers and the invention of the airplane. The first thing you should recognize is the airplane. They invented the airplane without a design manual, right? There was no preconceived design manuals available. So they had a lot of attempted flights, a lot of crashes. Finally, when they figured out how to fly, they went to the Army for more funding. And they took an Army captain up in the airplane and crashed and killed the gentleman. So just a comment on scale up and what happens in scale up. If I take a look at penicillin, penicillin was discovered 3 different times, 1896, 1928, and then in 1939. Penicillin is perhaps the most famous scale up because of World War II. They, in 1939, scaled up the process, and they probably had 2 million doses of penicillin by the D-Day landing in Normandy at that time, 1944. TiO2, titanium dioxide, is a white pigment used in almost everything. In the development of DuPont, TiO2 process, the research equipment kept on exploding again and again. Many times the researchers had to ask for money or funds to rebuild their equipment. And when they finished in the scale-up, the TiO2 process was essentially a controlled bomb. Right. So scale-up does have its hazards. NutraSweet was discovered by accident. Again, simply by luck. Present day, you have flu, swine flu, bird flu, whatever. These vaccines are limited by the method of production. How much you can make is limited by the method of production. Vaccines grown in fertilized eggs, chicken eggs typically. And I'm not quite sure how many doses of vaccine they get per egg, but the fact that they're fertilized eggs means that there is going to be a production limitation occur somewhere along the situation. Anyway, vaccines should be produced by other methods, so we can obtain much larger quantities. So there may be scaling up to insect cells in large tanks. These insect cells are a living item, so they have to pay a particular attention in keeping the cells alive. The famous quote from people who are in the flu vaccine area is, "It's not a question of if, it's a question of when." It's not a question that a flu pandemic will happen. It will happen. It's just a question of when. It's kind of an interesting statement. It's really a statement about funding. It says, basically, it's saying, please send more money. Right? Anyway, scale up is all about discovery. The lab creates a product, maybe a new material, and the desire is to make lots of it. The process needs discovery too. Expect a lot of failed attempts. It's very true. The other thing, again, I'll repeat, the process needs discovery too, right? Very important point that's often missed in scale-up is design. is a type of design, but scale-up is design. And most people who do scale up are not design engineers, right? So they have a tendency to do things that design engineers wouldn't necessarily do. The other thing about scale up, it tends to be goal specific. You want something, you want uniqueness. Anyway, so here's the scale up of the idea of the creation of wealth, right? But way back here in this back over here is the lab. Now, the lab people are very important because they are the ones who create the new product. And then the problem with scale up is that you have to make large quantities of that product. Now, there's lots of stories I can go into. One company made this really fantastic product, and their lab was sufficiently large that they could produce a large quantity of the material, which they sent out to their sales staff. and their sales staff sold all this product, all this material, and the company got these huge number of orders coming in. And then they realized they didn't really know how to scale up the process to make a whole bunch of this material. So that was a series of bad events, I guess. Good events, bad events. And they had a motto for this product. Their motto was, "We will make this product no matter how much money we lose." Right? You don't want to be in that situation. You will also notice that the lab people are not design engineers. Highly likely that they're not design engineers. It's also highly likely that they will change and scale up. The procedures may change. Whatever you did in the lab is not necessarily what you want to do on the full scale. You want to be able to have versatility in your design, be able to change things. So you find that scale up is not an area of lots of published formal information. Many companies and people don't give away their secrets or the history of their mistakes. The intent of this course is directed at some various technical aspects, approaches, science and engineering involved with scale up, and we will talk about some of the various methods used in scale up. But management considerations, you particularly should recognize the pilot plants are supposed to simulate plant operations. That's maybe yes, maybe no. Well, pilot plants have a variety of purposes, are varied with many purposes. Better product, lower production costs, more efficiency, earlier introduction to the plant, safety and environmental issues. And sometimes it's desirable to test or prove a process. However, let's go into timelines of scale up. Okay. Here with B is what might be referred to as the classic method of scale up. Okay. You have the lab that's developing something, and they finally found a new product, so they write a report on it, and they throw it over the wall, so to speak. And the pilot plant people come along and pick it up, do some studies, do some designs, and then some testing, and throw it over the wall. And then the plant design people come along and design the plant. Now, this may be considered the old German approach. Anyway, as opposed to that approach, perhaps this is a much better way of handling the scale-ups. You have the lab development people, and then simultaneously in the lab with them are perhaps scale-up people, engineers. The lab is filled with the chemists or the formulation people. The scale-up people are maybe equipment people. There should be a discussion going on between these groups. And communication is significantly important here. Communication is essentially lacking down here. In one case, going back to this for a second, this one group did lab studies on shaker tables, and they did extensive study on growing microorganisms in shaker tables. And the engineers over in the pilot plant were asked to scale that process up. Obviously, shaker tables, you've never seen a plant being produced. Shaker tables in a plant would be a pretty ridiculous plant. So some features in labs cannot be duplicated in a plant, and some features in the plant can't be duplicated in lab. Anyway, what that points to is there needs to be some communications between the lab people and the engineers or the equipment people or the scale-up people. And the scale-up people should continue on the process until it reaches the design plant design phase. And here there's also should be excellent communications between these two groups. Now this is a highly effective scale-up method, timelines, where everybody's talking with everybody else. And one company that was located in New Jersey had their lab in one town, and 20 miles further on there was another town that had the pilot plant facility. Anyway, immediately you know they have communication problems. Now this other method here, C, is quite an interesting method. You go directly from the lab into the into the plant. Now some people are very good. Some of these lab types, engineering types, plant people are very good. That sometimes, or oftentimes, they're quite successful. Supposedly in the old days, the New Science Group inside ICI, Empirical Chemicals Incorporated, British company, I think, in the New Science Group, they could take a fermentation process, I think, go right directly to the plant and do a very wonderful scale-up. Anyway, as opposed to that, there's another specialty chemical company that was doing lab studies, and the lab studies were going so very well, right, that they went ahead and did the scale-up into the plant without any piloting. And the plant was doing the first production run on this process, the first production material. And everything went well. All their process control equipment went very well. And as a result, they were figuring that all they needed to do was open up the valve and the product would come out. Well, they opened up the valve and none of it came out. So eventually they opened up the reactor, and the product was essentially goo, and it had balled up on the impeller in a significant manner. And it wasn't going to flow out of the tank. So the plant engineer calls up the lab and says, all this stuff balled up on our impeller. And the lab people said, well, that happened to us all the time. Okay, so again, that's a serious example of poor communication. The lab ran the equipment, apparently, or the lab ran the experiments. Plant people never saw how the lab people did their work. So you see poor communications. Second point is that plant person asked the lab people, well, what did you do about it? And the lab people said, well, we just picked up the reactor and shook it, and it came right off the impeller. Obviously, you cannot pick up a 10,000-gallon reactor and shake it to remove product from the impeller. So you have what might be referred to as non-scalable processes, shaking being one of them. Okay. So you have a chance for significant process failure when you're in this area and doing this. However, if you have very simple processes, like I would have to say mixing is fairly simple if you understand it, that can be scaled up. If, again, you have good designs. Without a laboratory or without an intermediate step for scale-up. Down here we have a situation where this is very true for almost everything. You have plant operations. They're going on. But they're not optimum, or there's a problem with it in the plant operations. So you take the operations, take it and do a scaled down study and do the testing. And then you do a process retrofit or a plant retrofit. Most plants are not fixed. They're always being retrofitted. The retrofits often improve the process significantly. So those are the various timelines that are available for process scale-up. Facilities, well, a pilot plant might be an intermediate step between the lab and the plant. Personnel and facilities, similar in some ways and dissimilar in others. Personnel, now this is kind of interesting. It's wise to have personnel that have combination of skills. Hopefully they have experience of what's possible in a plant environment, experience with day-to-day operations or problems that arise in plant. Then you need somebody with the thinking and experience of a developmental engineer and researcher. That's the other idea. And the third property is the experience and thinking of an explorer. If you're doing true scale-up, something that's never been done before, you will find that you're exploring, basically. And thinking and experience of a developmental engineer and experience in day-to-day operations. Those are a fairly unique set of skills. And the way you get those skills is you go to the plant and work there for a while. You go into development and work there for a while. And then you go into sales, perhaps, to identify new products that the customer may want. Okay, again, this is not again, actually. You need a full range of plant. You need equipment that will offer a full range of plant requirements. You don't want to hinder your studies. Objectives of the pilot plant, well, development, reliability tests on the process, equipment reliability tests, quality control tests, material usage tests, personnel requirements checks, safety and environmental issues. By the way, if you want to stop scale-up process, then you raise questions about safety or you raise questions about pollution. That will usually stop a scale-up. Then you have the plant acceptance issues and politics and cost analysis type thing. Plant acceptance, good idea. It lets the plant become acquainted with the process, allows the plant to run the process, witness process operations. Such operations permit an interchange with plant engineers and pilot plant people. You keep criticism to a minimum and you have introduction into the plant, which is quicker and easier. Environmental issues, again, we have said that. Personnel, safety, environmental, equipment compliance, personnel compliance. Then you can also perform cost analysis, verify pricing for the product. Again, you make a batch of material and you send it out to your sales force to see if product is desired. You're looking for cost overruns, potentially rat holes. You are trying to explore the number of operators you need. Maybe you wanted to explore material usage. Material should contain a full range of variability that the plant will be faced with, right? See, the chemistry labs often run reagent grade purity, and they have a set of results from those studies. However, the plant may be receiving their material in carloads, and the material quality is significantly reduced in the plant, and this can cause significant scale-up issues. So the laboratory should consider running their experiments or some of their experiments with plant-grade material or material that the plant's going to have rather than reagent-grade material. And you should always consider monitoring your feed. Funny story here is that you had a filtration process and everything was working fine. The filter aids were working fine. Unfortunately, one bag of filter aid contained a significant amount of fines, and that's essentially shut down the filtration process. Fines will shut down your filtration process. Here on the bag it says filter aid, but in truth of the matter, it is a filter hindrance. So you're adding filter aid thinking it's going to help, whereas indeed the opposite occurs. It hinders your process. Just because something's named something doesn't mean it's going to be that way, right? Well, there's a lot of mixers that don't really mix very well. Case in point, you stir your coffee with a plastic straw. You have this plastic straw, you have this very, very large cup of coffee, and the straw is a very poor mixer of your coffee. You will also note that that single straw is almost universal. Everybody uses a straw to mix a cup of coffee. Quality control. Can you meet the quality specifications? Demonstrate the quality levels can be attained, can be met. Equipment reliability. You're checking for equipment performance. Is it realistic? Is the equipment practical? What production levels are reasonable? What type of and rate of equipment failures are you going to experience? And what sort of preventive maintenance you're going to have. Process reliability is kind of interesting. Again, process reliability, you prove that the process is realistic and practical. You establish operating procedures for the plant. Again, you don't necessarily follow the procedures used in the lab. In fact, I would suggest you reevaluate all the procedures used in a lab. You establish startup procedures. You establish shutdown procedures. You establish the type of personnel you need. And you establish where control measurements. If you're going to have process control on your equipment, then you must determine where you're going to take the temperature reading, what flow rates do you want to have happen, or how you're going to make them. Development, yes, development. Run tests, analyze data, debug, do modifications of the process, improvements and changes, eliminates unforeseen problems, equipment redesign, retrofits. This relieves the plant from testing and permits experienced developmental personnel to work on the problems. Okay, methods for scale up. Okay. And go into this. Methods for scale up. Well, I have identified 4 different methods for scale up. One is repeating designs. It's very common, very standard method. It's not really thought of necessarily as scale up, but that's what scale up is. It's what it accomplishes. The purpose of scale up is to increase production quantities. Regular design methods. If you know your process and it's been around for an awful long time, where there's established rules of thumb, or excuse me for saying rules of thumb, established design calculations, then you just design the process. Whenever you design a heat exchanger, you run through a series of heat exchange calculations, determine the area of the exchanger, and then you determine what size tubes you might use. Then there's rules of thumb, which I hardly recommend. I do not recommend rules of thumb. And a schematic approach. This is, a systematic approach. This is what I would project as it's a thought process, basically. The method really depends upon a number of items: expertise, prior knowledge, difficulty of the process, predictability of the process. And quickly you run into equipment limitations. You should recognize that some processes are possible, some processes are not possible. Some processes are predictable, some processes are unpredictable. Scale up of an impossible process is not going to be successful, period. Scale up of an unpredictable process is going to be difficult, period. So let's go in and see what we have here in repeating designs. Okay. Well, first off, repeating designs, the process has been done before. Needs very little study. To satisfy the objectives of scale up, the process is simply repeated. There's nothing particularly difficult about this method of scale up. It's practical in many cases, easy to implement, and can be used for all types of processes. This type is often used first, which may be later scaled up by other methods. Example would be a packing line. If you're going to have a packing line, oftentimes the scale up would be just repeating that same packing line. There's no size increase, so in a sense, scale up is not really being accomplished. The added line is the same as the previous one. Throughput's doubled. There's very little reduction in unit cost. The quality is essentially assured. This method may appear to be too simple, but there may not be an alternative. Processes do not scale or process difficult to scale. Repeating the process is the only method left for larger production levels. As I said earlier, in a true sense, scale up is not done. Production, however, is increased. New processes may be difficult or impossible to scale up to larger sizes due to a number of reasons. Repeating is a way of obtaining larger productions while not doing scale up by increasing size. Some examples of repeating design, they're everywhere. Roller bottles in biotechnology. Basically, you have a roller bottle which has been used in a laboratory, and you have performed studies on how to grow biological material in rotating or roller bottles. You know how that works. Now, on scale up, you just buy 100,000 roller bottles and proceed with your plant operations. However, that can be quite labor intensive. Precipitation reactions will have a scale effect in them. Precipitation reactions, what's meant there, you add a stream to a batch of liquid and you form a precipitate. How that's added determines the particle size of the precipitate, or it influences the particle size of the precipitate. You have motor sizes, okay, as a possible, You have motor sizes. The largest size motor is 6,000 horsepower. You get above that, then you have real difficulty in the size of the motor becomes very large. Acceleration machines. These machines might be machines that produce pills or tablets. Okay, they can go only so fast, after which they'll shake apart. If you watch television, you see these circuit board machines where you have this very rapid moving around above a circuit board as they operate on the board. You can see that those machines are acceleration machines, And they have an upper limit on how fast they can actually go before falling apart. Spray nozzles and atomization, you reach, what happens is the nozzles on scale-up require such large pressure drops that become unfeasible. And so as a result, you, instead of having one big nozzle with very high pressure drop, you have 3 or 4 smaller nozzles that satisfy the needs. Tubular reactors, example, food lines. If you have a roller, a crushing grinding unit, perhaps you're increasing the length. If you watch how they produce jelly beans, right, you'll find that they'll have what they call pans, machines that hold the jelly beans and spin the jelly beans around for coating and sugar addition, wax addition. Anyway, instead of making a very large pan, they will have 10 or 20 smaller pans lined up. In fluidized beds, scallop fluidized beds, it's usually just add more bed area. So here's a brief example. 100 roller bottles, 6,000 horsepower. Tabulating machines, presses have acceleration limits. Atomization is limited by very high pressure drops. Single tube reactors are scaled to a shell and tube heat exchanger. Food lines and cafeterias are required to service more people. You just add another line. Processing rates through rollers are increased by increasing roller length. The couple of things you should recognize here. Practical restrictions are often encountered during scale-up. Limitations to scale-up for some of these processes are due to equipment limitations. If practical restrictions are encountered, then repeating the design is a legitimate alternative for other scale-up techniques. Some processes are not very well understood. Scale-up can be considered uncertain at best. Particle systems have the reputation of being non-scalable. Examples might be precipitation reactions and crystallization processes. So when you study these non-scalable processes, you have laboratory studies on those, you will find that laboratory studies may not be useful to represent plant behavior. If the lab and plant do agree, it's only fortuitous. It's only a matter of luck. And oftentimes, some processes, for troubleshooting purposes, need to be studied in the plant. Fast precipitation reactions simply repeat the small-scale process accurately. This may be key to the successful scale-up. By repeating the design, conditions similar to those of laboratories may be attained, as the process results should be similar. So, another big item about repeating designs, it does not require extrapolation. Scale up is extrapolation. You are taking things to much larger sizes. If you don't take things to much larger sizes, then you're not extrapolating. Extrapolation always can lead to uncertainty about the success of your process. Many scale-ups require extrapolation of data, information from one size to another. The certainty offered by repeating designs is an advantage to this method of scale-up. Another advantage is you don't have to understand the process. Very, very interesting statement. You don't have to understand your process since you already have a working unit. And you'll find a major limitation to scale-up for many, many processes is the lack of data and information about the process. Some difficulty or impossible processes will eventually be overcome. In biotechnology, mammalia cells in the past were sensitive to high shear. Newer cells are less sensitive. Okay. This enables scale-up designs to use more traditional process equipment, like batch tanks instead of roller bottles. While repeating small-scale processes is a way of handling non-scalable processes, there are processes that are non-scalable. The method is not very efficient. There is no economy of scale, and processing problems may not be solved. Okay. Perhaps we take a couple seconds here to rest a bit, and then we'll charge ahead. Anyway, let's go on. Regular design methods. Now, processes that have been studied or well studied are simply designed. An example of that would be shell and tube heat exchangers. However, you should recognize that there are just different design methods out there for everything. Oftentimes, there are different design methods out there. And for the shell and tube heat exchanger, there's two major methods. One's the Kern method, and one's the Bell-Delaware method. The Kern method is, say, before 1950, and the Bell-Delaware is probably after, say, in the 60s. So there is an age difference in these methods. Kern method is older, less accurate, conservative, whereas the Bell-Delaware method is more accurate, or it claims to be, resulting in less conservative designs and resulting in better performance. Anyway, Bell-Delaware method has been incorporated in many computer-based designs. Take, for example, Aspen. Aspen incorporates the Bell-Delaware method. Basically, getting the weeds here, getting the details, Bell-Delaware method treats the shell flow in much greater detail than the Kern method. The Kern method is well entrenched in the undergraduate textbooks. The Kern method is easier to use and understand. It took me about 30 days to make sure I understood the Bell-Delaware method thoroughly. Many alternatives can be generated quickly based upon computer designs. That's very important. If it's computerized, you can start varying and asking different questions about different variables, which is very, very useful. Unfortunately, heat exchanger design is well established. Although heat exchanger is well established, unpredictable behavior still occurs. Fouling is notorious for being unpredictable, okay? And fouling levels cannot be accurately predicted. Even with fouling studies, without some fouling studies. Fouling is always a problem in the design of heat exchanger, and this is a significant level of uncertainty in the design, right? You're assuming no fouling. That's a bad assumption. Everything fouls. Fouling is similar to having your dentist clean your teeth. Your teeth foul over a period of time. Shortcomings of the design have to be handled by the plant. Shortcomings of the design have to be handled by the plant. Another aspect of unpredictability comes from design procedures, right? The research for Bell-Delaware was from 1945 to 1960, and during these times there was only a certain types of heat exchangers studied. Today these designs are quite different. So you have evolving designs. In an effort to get most out of shell and tube heat exchanger, flow velocities have been increased. Heat transfer increases with velocity. However, your mechanical design can take, however, whether your mechanical design can take such high velocities is another matter. You increase heat transfer, but you also increase mechanical vibration. Sometimes the tubes of the heat exchanger simply vibrate out of the tube sheet, and the heat exchanger only lasts for several hours. A heat exchanger can be $1 million. So even well-studied areas of engineering will have uncertainty in designs. Many designs have considerable uncertainty that's not recognized. Many designs may go into regimes that have not been studied. Many unpredictable design variables are very predictable after studies have been made of them. Design should be simple, robust, nimble, and selected for easy cleaning and inspection. Data on cleaning may only be obtained from plant environment. Cleaning issues are rarely addressed in the plant. In the lab. I was visiting Merck, which is a drug company, and I was sitting across the table, and the design engineer, or the engineer, said he didn't care what about this or that. What he cared about is whether he could clean it or not, and that's critical. Cleaning can be quite critical for some materials. Should always have available design options. Regular design methods are always preferred. Should be used when available. Fortunately and unfortunately, they're often packed into a computer design package where fill-in-the-blank procedures are used. Questions of design accuracy seldom arise. Everybody believes a computer. Can you imagine that, believing a computer? Some companies have initiated studies to determine design methods for heat exchangers. This is company specific and seldom appears in forthcoming open literature. The question of design accuracy can only be answered thoroughly by industry. Scale-up needs and concerns occur most often in areas that do not have regular design methods. Testing is often used in the scale-up process and may be done at the pilot scale. Testing for fouling and in the plant scale and the plant environment is most desirable. So you're more apt to test and test and test and test some more, basically. Safety factors. Quite an interesting area, safety factors. Useful and mechanical aspects of design. Typically, mechanical engineers will use a safety factor of 1.5. Maybe you should go with 2.5, right? Just from the point of view that you will probably be pushing your equipment. So we're going to put in here mechanical aspects of the design should be beefed up. Quote from Mobil Oil Corporation before they were part of Exxon. Basically said, if we ain't burning, we ain't learning. Well, what that means is if we're not pushing the equipment, we're not learning anything about our equipment. You should always consider safely pushing your equipment. If I go to Europe, the Europeans are very precise people, very, how can I put it, different from Americans. Then when they design something, they want to run the equipment at the design specifications. In the United States, however, running the equipment at the design specifications was what was being done 3 years ago. They've pushed the equipment out of bounds or beyond that by a considerable amount, and as a result, they're making more profits. Again, the idea of scale-up is to make profits. You should always consider pushing your equipment. You should challenge process myths. We'll talk a little bit about process myths later. Okay. Rules of thumb? Well, okay. Basically, everybody's seeking the secret by which scale up can be done. It's such a broad area, crossing many disciplines. There's no universal rules of thumb. Typically, you're interested in capacity and throughput and power requirements. And usually you find these are given. The data, unfortunately, may not support some of these rules of thumb. Some of the things you should watch out for is whether rules of thumb are not, many rules of thumb are not dimensionally correct. Others are based upon inaccurate process physics, poor data, extrapolation of poor data. Process physics should not be properly understood. Or, excuse me, process physics have not been properly understood. All right, poor data leads to poor extrapolation and poor scale-up. Scale-up relies on extrapolation of process data, physics, and data. To use a rule of thumb effectively, one needs to have good process sense. Good process sense. To obtain good process sense, it takes time. Okay. Here's an example of data, right? Now, if I take a look at this, I have capacity over here and I have geometry down here, which, by the way, capacity and power input, right? The biggie that's missing here, the really important one, is geometry. Well, typically, if you have the equipment, you have the geometry. But we should be very sensitive to geometry. There's three types of process variables. There's fluid properties, there is energy levels, and then there's geometry. Of the three that's important, geometry is the most important. Okay? Anyway, so we have this data. Now then, we need to take a look at this data. Let me switch over to our slideshow here so I can bring this out a little bit better. Okay, I'm looking for my options here. Now then, if I take a serious look at this data here, there's a big void region up in here. And if I come down here, there's also a big void region right in here. And if I redraw that line, let's just see if I can change color. Let's change it to red. If I redraw that line, I'm coming down like this. I'm not very good at this, obviously, right? The slope of that line is a lot steeper than the data indicates. The slope of the line is a lot steeper than 2, right? I think the slope of that line is more like 3. So I don't know where this actually comes from. I'm sure that this is quite reputable data. It's not meant to deceive anybody. But this is the idea that you should always question things. That difference between 3 and 2 will significantly change the design. Okay. Significantly change the design. And the approximate capacity, right? Again, the diameter is very important, i.e. it's geometry. Let's see if I can get out of here. I guess in show. Go back. Discard. There we go. So, I conclude. Rules of thumb may be traps. Here's the rule of thumb. That could be actually 3 rather than 2. And when that happens, the scale up significantly changes. Believe me, we'll show that later. Small changes in this exponent can be significant. Well, 2 going to 3 is pretty high change. Anyway, rules of thumb may be traps. Rules of thumb should be avoided. Should address process physics, capacity and throughput, power requirements for dimensionally correct, based upon accurate process understanding, and it takes time to understand your process. Now, books that were cited here, references. This is an excellent book by Wallace, Process Equipment, Chemical Process Equipment. This is 1988, if you can get the original. See, there's 2 or 3 versions of this, and the one is 1988, right? And then we have Gupta working with heat exchangers. If you're into crushing and grinding, you might try that book. And size enlargement by agglomeration, you might try that book. Now, let's try a systematic method for scale up, since we've talked about this a bit. I'm checking my battery on my computer to see if it's up to snuff. That may limit my presentation for today, as my battery life. So let's explore the systematic method for scale up. And quickly we see there's method to the madness. What we want to do is focus on methods of scale up that are more systematic and exploratory. These methods might be followed for an entirely new product, new process, or a process retrofit. See, we may be scaling up, but maybe we're also investigating a process retrofit. For a new product or process, there's a new product and also a new process. The risks can be high. Hopefully, this will help reduce the risks involved. First thing you ought to recognize is that processes have needs. It's very important. If you have identified the needs typically used in design, then perhaps you will mislead yourself. Often needs are expressed as size or duty, but I tend to want to think about, instead of size or duty, or I think more in a global sense, the needs. Needs must match the process objectives and must match the processing equipment. Needs will generate the objectives, and the equipment fulfills the objectives. Anyway, so if I go here, I see the lab, the pilot plant, and the plant. And I see the designs that was used in the lab, pilot plant, and the plant. And I see process needs also happening here. So, first off, let's point out that we have the equipment sitting here, and the equipment has certain sizes associated with it. So that's what I mean by scale, certain size, velocity, diameter. Anyway, first thing you want to note is you don't have to use the same equipment on scale up. Now, there's a whole how can I put this? There's a large amount of people who believe in geometric similarity. Well, that's fine. Geometric similarity is a useful concept, but you do not have to use it. It's not required to use it and scale up. You can use it, but you don't have to. You are free to change the geometry. You will also find out that when you change the geometry, you can improve the process as you scale up. Okay? So the whole idea is you don't have to use the equipment the laboratory used. You can change the equipment in the pilot plant, and you can do further equipment changes when you go to the plant. Okay? Very important point. You want to improve the process as you scale up. That's very possible, number one. You don't have to use the same equipment geometry. This concept of geometric similarity is okay, but it also leads to suboptimum processes, basically. Now then, let's go on to needs. Process needs determine the process. It's very important to recognize these needs determine everything. There should be one design and one design only that's optimum, okay? And your job is to find out what that is. But the needs of the laboratory are quite different than the needs that the pilot plant people have. It's quite different than the needs that the plant people have. So needs will change as you scale up. The problems will also change as you scale up. If you're looking for the process to remain the same as it scales up, you could probably forget about it, okay? The process will change on you. And you should be aware of the possible change and take advantage of it. So some needs are in the lab, the lab needs disappear in the pilot plant, and new needs appear. And when you go to the plant, the pilot plant lab needs may disappear, and the plant has its own set of needs. So you have varying equipment and you have varying process needs. And these should the process needs should really need to be written down. Now then, the needs are satisfied by equipment at each level. These needs are satisfied by the equipment. So you're going across this way. Process needs are satisfied by that equipment. Process needs are satisfied by that equipment. So equipment can change on scale up. Process needs can change on scale up or scale down. So there you have it, the scale up process. Did I cover that? Let's go back one more. They're very important here. The process objectives become the wish list. Process objectives become a wish list and performance indices for the process. Process objectives become the performance indices for the process. They also are what you want the process to accomplish. So needs and objectives determine the process. Needs are matched with the equipment and operating conditions satisfy those needs. If the needs are not met, the objectives are not accomplished, and the process simply limps along or fails entirely. Usually it just limps along. Failure entirely would be great because that will force you to reanalyze everything. Scale up is the same as needs matching at each level. Laboratory equipment and operations satisfy laboratory objectives and laboratory needs. Pilot plant and plant equipment must satisfy the objectives and needs of the pilot plant full size. Needs, objectives, equipment, operation do not have to be the same at each level. They don't have to be matched between scale levels. Needs and objectives and technical problems may change with scale. Some may disappear and new ones appear. For example, foaming. Foaming in the laboratory can be notorious, right? On scale up, the importance of foaming may be significantly reduced. Foaming occurred in the lab, but doesn't occur in the pilot plant. It's hardly ever seen in the plant. If you look, an example of needs matching occurs with the addition of a powder to a liquid. Okay. Typically here you have, what did I do over here? There we go. So here we have powder up here going through a sifter that will create a cloud of powder, right? And each powder particle is separate. It's been separated out from the lumps. The lumps have disappeared and it's all single particles. And the number of surface variations, or the number of surface undulations, will match the number of particles. So you have a size matching going on, matching of sizes. And at the same time, the concentration of particles will match the concentration of the surface undulations. So what happens in this device is the size of the surface waves matches the size of the particle, right? The number of waves matches the number of particles. Processing is done one particle at a time. That's what's necessary. If the particle is not done one particle at a time, you will form lumps. It's very possible that if without the sifter, that you could perhaps have lumps that are formed in the falling liquid curtain. Now then, I'll show you a falling liquid curtain here in a second to see if I can bring this up. Okay, let's put this in the background. And let's go to falling liquid curtain. Where you be? R.D. Barinko. Where is R.D. Barinko? Right here. Now I'm not quite sure where it is inside here. Let's try that. Here you go. Let's try that. There is a ring here all the way around, and liquid is coming out of that ring and falling through the piping and discharging in this area here. And you can see that the surface undulations are significantly large number of them, and they're small, and they're matching the size of the particles. And so that's happening inside here. See, if you didn't match the different particles, you have a situation where you add powder to the liquid and you have these lumps. These lumps. Two situations that I ran into is that, actually only one situation. I mentioned the company, but I won't. They had an 18-hour cycle time for their batches. So they had a powder addition. The procedure added powder. And what then happened is the powder formed lumps. In other words, the procedure and the way it was carried out caused a processing problem. It took 8 hours to get rid of the lumps. Then further on down in the procedure, they had another powder addition. This powder addition, again, they made lumps, and it took them 4 hours to mix away those lumps. So the procedure made the problem, and the procedure subsequently solved the problem, of course, all right? But you must realize in solving the problem, there were 8 hours wasted dissolving lumps, and then 4 hours wasted. So an 18-hour procedure, 12 hours were spent dissolving lumps, which should not have been made in the first place, which should have not been made in the first place. Okay? And again, we've seen the falling liquid curtain. We see the sifter here. By the way, you won't be able to buy this piece of equipment because very few of them have sifters up here. You know, in your kitchen, you have a flour sifter, and the flour sifter sifts flour. And you can take that into the plant or inside your company and use the same concept. Sifting flour at home is very similar to sifting powder in the plant. What's really amazing is the physics in the kitchen, in cooking, however you do it, is very similar to the physics in the plant. So it's very easy to be able to think more clearly about your process is if you make a kitchen analogy. Processing is very similar to what happens in your kitchen. So we are needs matching. Here we needs matching by matching the scale of the material to the scale of processing. Lumps It was one we went in and replaced in their procedure, we replaced how they made the powder addition, essentially dumped in the bag. But now the powder is being added through this device, sifter, falling liquid curtain, stator rotor device. And their cycle time went from 18 hours down to about 7 hours, right? The powder additions were handled in half-hour increments. So the first powder addition was half an hour. The second powder addition was a half an hour. In other words, again, the procedures that have been used in the past should always be reevaluated in a process retrofit, perhaps. And so there you go. Lumps are not the same as surface waves. Matching's not done, so you had significant cycle time. Was one of their, for the company involved, this was one of their major products. So stop, think about it. We reduced the cycle time from 18 hours down to 7 hours. So we increased production by, what, 300%? They were producing one unit. Now they're producing 3 units in the same amount of time. That's a pretty good increase in production on a very valuable product for them. Anyway, and it's also something, it's an example of a process retrofit. You were dumping the bags, making lumps, and now they got rid of them. So I would suggest you write your needs matching statement. Some of these are, I need the same drop size between the pilot plant and plant operations. I need to cook. I need the cooking rate to be the same between the lab and the kitchen, lab kitchen and pilot plant facility. I need the mass transfer rate to be the same between the small fermenter and production. I need the same interfacial area per volume to be the same. These are all pretty much English statements or language statements. No mathematics here, but you can take drop size, change it into a mathematical variable, cooking rate as well, mass transfer rate as well. Obviously, another example is needs matching is when you hook up equipment. The equipment must match other equipment in the process. The output of one unit operation must become the equipment, the input for the next operation. You want a good match between the two so bottlenecks aren't formed. If you're going to have a bottleneck, you want it to be the first thing. Scale up is needs matching at each scale. Needs matching is fundamental to process understanding. Needs of the process well understood, many processing problems would not occur. The needs of the process were understood, processing problems would not occur. Okay, what do we got here? Okay. We've been lecturing, I think, for an hour and 15 minutes. I'm not quite sure how long. But anyway, let's persevere here and hit these major points. Some major concepts is process similarity, geometric similarity of simple unit operation. You're always worried about energy input or power input. We're also very much interested in geometry. So working volume, where is the process actually taking place? And the important scale-up ratio, that's very, very important. Process similarity is what I seek on scale-up. And it basically says what I did in the lab is what I want to do in the plant. Or what I did in the pilot plant is what I want to do in the plant. Right? Two processes accomplish the same objectives by the same mechanism making the same product. That's usually what I call process similarity. Scale-up objective is to obtain this between two scales. Process similarity is that on scale up, whatever the process occurred in the lab, make the product, the same process should occur in larger units. Again, we may qualify this. We may have an improved process should occur in larger units. Again, we may be targeting the fact that we want to improve the process on scale up. And hopefully we'll show you one or two of those examples. Oh, here it is. Hopefully the process can be improved on scale up or during scale up. Geometric similarity applies to equipment and uses the same geometric shape for the large scale as was used for small scale. Large scale equipment is just a magnification of smaller scale equipment. Geometry and proportions of all scale are simple multiple scale factor. Could be expressed as a length or volume. For pipe flow processes, geometric similarity is simply by increasing pipe diameter and basically stated as a factor, length factor increase. Well, for a tank, however, you simply enlarge it. Now, what you have here is the process geometrically similar process assumption, right? It's often assumed if the same geometric equipment shape is used on scale up, then the process similarity will occur. That's not true. This is an assumption and is often a wrong assumption. If you assume geometric similarity, you may not have process similarity. Geometric similarity is both a curse. I'll just put it like this. Let's be positive. Geometric similarity is a useful tool. However, it is also a curse. It's both useful and disastrous at the same time. That's the way life is. Sometimes it's this way and sometimes it's that way. That's the way life is. Anyway. Geometric similarity does not assure process similarity. Process similarity is what you want. And I will also add that geometry is a highly significant. As I said, there's three major variables: properties of the materials, energy level, and geometry. Of those three, geometry has the most important, or is the most important. So, I would always want to seek improved geometries as I scale up. Here it is. Simple process, material, energy, and geometry, right? Mistakes in material, improper energy level or power levels, inappropriate geometry. Well, this is where all the mistakes are happening. There's only these types of mistakes that can be happening. Well, energy or power to a process is what makes the process go, or what drives the process. Without energy or power, processing would stop. Energy and power are fundamental to the analysis of the process, and energy and power per time is the only quantity a fluid element receives. That's very old fluids theory. Here I have a little particle of material in three different vessels. The only thing it sees is energy. So it doesn't realize it's in an agitated tank or a static mixer or a packed bed. It's just an individual particle here or chunk of fluid here. It doesn't really matter. Energy, there's energy levels. Very low, or I should say, since the energy levels on these processes is very poor, you oftentimes get poor performance. Bubble columns are notoriously poor, right? Then you get way up here to Branberry mixer. This is the device that puts carbon into rubber. or perhaps a co-kneader. These are tough, very tough machines. Simple bubble column going to very, very tough machines. Co-kneader is a device that rotates and reciprocates back and forth. It rotates and reciprocates. Now, microfluidic devices are very interesting and very much, from a point of view of the cosmetic industry, or in the point of view of lotions, it would be interesting to see if microfluidics devices do not have a role to play in these industries. You have substantial pressure drops occurring, 40,000 psi pressure drops in these devices. And they can take oil and water and make single fluid. Let me say that again. They can take oil and water and make it a single fluid. So they mix all the way down to the micromolecular level. Now, further on, we're going to introduce the concept of worker. And worker is energy or the power input. And it's very important in many processes. But energy and power are not important in some processes. Mixing does not depend upon power input. Mixing does not depend upon power input. Mixing does not depend upon energy input. Finding the right energy level is often critical for processing. Finding the right energy level for the process is key. Okay. Actually, skill up amounts to trying to figure out or trying to determine what equipment is the best to use. Right? You're trying to find the right equipment for the job. That's a very practical concept, Obviously, you use a hammer to pound in a nail in a wall. You have a wall, you have a nail, you have a hammer, and pounding on the hammer, on the nail with the hammer works very well. However, if you take out a screwdriver and try to pound the nail in the wall with a screwdriver, obviously, it's not nearly as successful as you would like. So there's an example of process where the geometry is key. And you'll find that that runs through all of Scale Up. Geometry, equipment is the processing geometry. Equipment must match the process. Alternatives are also discussed, where processes are fitted into the equipment. Now, that's really a bad way of doing it. You have your process. You look at your process and design the equipment to meet that process. Just the reverse is often done. You have the equipment and you force the process into the equipment. So, anyway. If the right match has been made, then processing objectives or the processing geometry will enhance the objectives and performance. If the wrong match is made, i.e. you're going to get a screwdriver to pound the nail in the wall, process objectives and performance will suffer. Some geometries are very effective at accomplishing a certain type of processing. Other geometries, not so much. Other geometries are not successful. So you have, it's pretty funny, the piece of equipment says mixer on it. You read on the boilerplate mixer, but it doesn't mix. Or it doesn't mix very well, okay? So you have the situation where, yes, it may mix, but generally speaking, it's not a very good mixer, even though it's called a mixer. Okay. I'll show you examples of that later on. Well, I'll just maybe show it to you right now, I guess. Slideshow from the current slide. Okay, this means I can draw over here. Okay, I'm looking for a highlighter. One of the worst mixers in powder-powder mixing is the V mixer. All right? And it's used by the pharmaceutical company. So this thing rotates around, right? What happens is on this side, it's all mixes up very well. And on this side, it mixes up very well. However, there's a plane of symmetry right down the middle where there is no cross mixing, right? This doesn't happen. So this becomes well mixed and this becomes well mixed, but there's no cross mixing between the two. Now that's very poor geometry, right? However, we can redo it up here, and we change the geometry. Again, changes the geometry up here, where we put cross baffles in this powder mixer. I guess it goes like that. Anyway. And what happens is when the particles tumble down, hits this baffle, it gets put over in here. And when the material tumbles down and hits this baffle, it gets thrown over here. So by changing the interior baffling arrangement on this V-cone mixer, you can substantially improve the mixing performance. This mixer is sold everywhere, right? You can probably buy one on the used equipment market. Not a good mixer. Put internal baffles in there, excellent mixer. Anyway. So moving right along, for reactor design, reaction kinetics are matched with the best geometry. Reaction and its kinetics are matched to the best geometry. This enhances the desired reactions while limiting or preventing undesirable reactions. Anyway, that's a comment. We'll talk about that in a second. However, the important point is, finding the right equipment is key to processing. Finding the right equipment geometry is key to processing. Working volume. Working volume is where the process takes place. Scale up often fails because working volumes is not identified. Other volumes may be inventory volumes waiting to be specified or waiting to be processed or have already been processed. So let's take a look at our chemical reaction here, right? One of the interesting things about chemical reactions is it's not a well-taught area in universities. The reactor design is not well taught at all. Okay, but here we have a typical multi-phase reaction. And if I had tried to identify where my reaction is taking place, take a look here. Give me some color here. First off, I should realize that the reaction can actually go up the feed pipe and out. Now, that would take an extremely fast reaction, but nonetheless, it's quite possible. Right? The reaction could be, it comes in and the reactor is the reaction is occurring right around the feed plume. It could be that the feed comes in, leaves, exits, and then reacts over here. This is very common, by the way. Feed comes in, leaves the reactor, and then reacts. An example of that is a car backfires. The gasoline comes into the engine, leaves, and then ignites in the muffler. So these are physics that difficult to determine, but can very easily happen. Then we could have a situation where we worry about the slurry concentration. Okay? Where is my thing? So we're interested in the surface area of the solids here. The reaction takes place on the solids. We also note that there's two reactors here, one a clear area up here that has no solids, and down here we have a clear solids concentration down in here. No solids, high solids. That means two reactor environments, two different sets of chemistries that can actually take place. And this is one of the reasons why pharmaceutical companies want to make sure their solids go throughout the entire tank. Now then, endothermic reactions will probably take place on the surface area of heating coils. Right? If I have bubbles and drops, the reaction may occur on the surface of the bubbles or drops. The reaction may actually occur in the feed pump. In this pump. I feed before the pump, it gets recycled up, and a pump around loop gets sprayed in at the top. The pump may be the reactor. What we're talking about is trying to understand the process physics and where the physics is happening. Once we understand that, we have a much better chance of understanding reactor design. And from what I would gather, the idea of what is taught in undergraduate school is a reaction occurs throughout the reactor in a homogeneous manner. Well, that may be 5% of all reactions out there, right? 25% is between a gas and a liquid. So you can have all kinds of places where the reaction is occurring. It does not have to be, or it doesn't necessarily occur like you were taught in the university. You can always be, I'll never forget my organic chemistry professor. I didn't believe half of what I was taught in organic chemistry. It appeared to be a lot of memorization. And I kept on asking him about the other possible reactions that could take place other than the one he was talking about. And he told me several times during the course of the organic chemistry course, that the reactions only went this way and side reactions did not occur. And it's only recently, in the last 20 years, I come to an understanding that that chemistry professor lied to me, right? Lied to me, my goodness gracious. Turns out that if you have complex chemistries going on, you have the potential for lots of side reactions, and you wind up with a whole soup of products. And our job in the reactor business is try to minimize the side reactions to optimize the production. I don't know if anybody's into reactions, but anyway. Reaction. Where is the reaction? Important ratio. This is the most important thing about these notes. A major problem in scale-up is the matching of the size of the worker to the size of the job. The size of the worker is what's doing the work, accomplishing the process. The worker may be processing area, it may be power or energy input. The size of the job is often the process volume. Not always, but often the process. So on scale up, you want to keep the ratio of worker to the size of the job constant. You want to identify what is actually doing the work that's important in your process. What's the physics of that? And then what's the size of the job for that? Or what is the size of the job? If I go back to my reactor, if I have the reaction occurring around the feed plume, now that's where my reaction is occurring. And the volume of the feed plume is the volume of the size of the job. So, that's a very important ratio. This scale-up mistake occurs often when you fail to recognize this ratio, or this ratio is not identified. You got to establish what's accomplishing your process, what's the size of the job. Now, equals constant. Now, to make your process or improve your process, you want this ratio to be greater for the plant. You want to have more worker per volume on scale-up than what was in the pilot plant or what's in the lab. Okay, if I go back here, this identifies some of the workers in this reactor. Well, the surface area of the plume is probably the worker. Surface area of these heating coils for endothermic reactions may be the worker. The surface of the catalyst particle may be the worker. So if I look at this, I have a lot of different types of workers, so to speak. And again, to improve the process on scale up, you don't set it equal to constant. You set it a little bit. This for the plant should be larger than this for the pilot plant. So, general scale-up method. Okay. General scale-up method is based upon the idea of process similarity. The objectives is to design a working large-scale process. The first step, there's various numbers of steps here you go through, and the first very important step is you're trying to seek process similarity. What are the important aspects of the process? What is being attempted? And you have to ask the right questions. It's very important. You got to ask what the right questions are, and you should know what your objectives are. It's not uncommon for me to walk into a plant and have the objectives not clearly identified. Aha, there it is. Objectives are often not known, or they're not agreed upon. Then you go and see what is doing the work in your process. What is the controlling mechanism? What's the process physics? Where is the process occurring? And down here we have the right physics and chemistry. What are the process flow regimes? Is a simple question. Flow regime is a description of how the flow behaves. So in here you have to have what I've called the right science. Actually, what you need to have is the right science and the right equipment for the job. There should be an addition in there, right equipment for the job. At this point, we're going to use geometric similarity. We should recognize that geometric similarity only serves as a starting point. We should recognize that geometric similarity is only a starting point. It may be quite good when it turns out. Then from various data correlations, scale-up methods obtained. Geometry is obtained by similarity, geometric similarity. Operating conditions are obtained from data analysis. So you sit there and you make a judgment. Okay. What is a judgment's made as to whether the scale-up is appropriate. The results, are they reasonable? Can the scale-up be accomplished? Will it be a working design? If yes, you want to stop or explore it, do some scale-up work, verification. If no, then you go to other options. And these other options I have included have been called Plan Bs. Go to Plan Bs. The important thing is you don't accept no for an answer. No is a word that you only encounter on the way to a yes. You're going to get a working process. No means the process does not work. Yes means the process works and you're finished. Okay? Scale up is design. And this is more or less a sort of a scoping level design. A scoping level. More detailed design can be added later. Substantial details have to be added. Okay. Plan Bs are very important. Significant number of your proposed scale-ups will turn out to be impractical or impossible. Options are then used to take a different approach to obtain more practical results. Scale-up options reduce uncertainty and risk. Small-scale studies should provide guidelines for process scale-up. Examples follow. So, there we have it. And now it's 12:48 and time, and I started, I think, at 11:13 or something of that order of magnitude. So if I get another 25 minutes to make it a full 2 hours. Okay, let's try the burning problem. Small scale, we have 1 liter. Heat transfer is occurring. Studies have been done at higher levels of agitation that does not have burning. What can be done to prevent burning of the material as we move into the pilot plant facility? So we're going from 1 liter in size to 100 liters of size. State the process objectives. What's important aspects of what's process similarity you seek? What are you trying to do? That's very important questions. Obviously, you have burning. Okay. Process has significant problems with burning. Process similarity is that since the material did not burn in the lab, in some cases the material should not burn on the large scale if scale-up of these conditions are done properly. So your objective is to prevent burning, So what's doing the work in the process? What's the controlling mechanism? What's the size of the job? Well, agitation has prevented burning. This has been done by increasing the heat transfer. So actually the work is being done by the heat transfer coefficient. Okay. So we go over here, and this establishes what we're trying to do on scale up. We want the heat transfer coefficient scale 1 to equal the heat transfer coefficient scale 2. The volume change is 1 liter to 100 liters. So 100 in volume or 4.64 in length. If I cube this, I will wind up with 100. What are process physics and chemistries? What are the process objectives? The process chemistry is that burnt product. Chemistry is not important in this case if burning is prevented. Process flow regimes, turbulent. We didn't talk about flow regimes. At this point, we're going to go with geometric similarity. We go to our heat transfer book, scale up method. For heat transfer coefficients, we have this thing right here. Nusselt number is equal to some constant times Reynolds number of 0.66, Prandtl number of 0.33, and a ratio of all viscosity of all 0.14. Now we're going to remove all fluid properties. So we go through the Reynolds number, Nusselt number, Prandtl number. They're all the same fluid properties, so they cancel. We're going to also assume this constant remains the same on scale up, and the exponents remains the same on scale up. So and we throw away the viscosity ratio because that's going to remain constant on scale up. Okay. So when we do all that, the heat transfer coefficient was buried in the Nusselt number. H is the heat transfer coefficient. D is the diameter. It's proportional to N. D E squared and the 0.66 power. This is the Reynolds number. So what we have here is operating variables, which is a rotational speed. And we also have geometry, which is diameter sitting there. We have a process result, which we want. And away we go. So the heat transfer coefficient varies as the rotational speed of the impeller to 0.33, the diameter of the impeller. So going through here, we know that H1 equals H2, so scale 1 is equal to scale 2, basically, right? And here I have substituted in scale 2 of 0.4 times the diameter of scale 1. So the diameters will cancel out, right? Relationship between rotational speeds is now obtained. In other words, I know what scale 1 was, and I know this equation relates scale 1 to the rotational speed scale 2. So I can calculate the rotational speed scale 2 now. And with rotational speed scale 2 is equal to about half the rotational speed scale 1. Okay. So from the rotational speed, N2, and the diameter of the impeller, I can determine the motor size for the pilot plant. Material properties remain the same and cancel out. Remain the same on scale up. Geometric similarity was used, so that lets me cancel out geometry ratios. See, that's the advantage of geometric similarity. It lets you get away with being slack, so to speak. You don't have to worry about it if it's held constant. Ratios are the same, small scale, large scale, they cancel. Next thing is to judge the results. At this point, a judgment is made as to whether the scale up is important or not. If yes, it seems to be yes, it looks reasonable. Half the rotational speed scale 2. I really don't know if it's going to be actually okay, but it certainly looks like I should do some testing on it to see if it works. Yes, the geometry is the same. Operating conditions is fixed by the procedure. The working design, we have to go yes. So the answer is we can stop till we test this out. Other designs are not needed. Some concerns, some items of concern here. First, the material properties may change on scale up, and this change may have to be accounted for in scale up. Second, the assumption is the correlation was assumed to hold between both scales. The correlation 0.66 and the lead constant, we assumed that was the same for scale 1 and scale 2. Yeah, that may not be true, but it's a good starting point. The origin of the correlations from boundary layer theory, that's a little bit significant there. We'll let that one ride until later. And by using the correlation above, it's assumed that the heat transfer similarity between the lab and the plant. Boundary layer the boundary layer in the pilot plant equipment may be different from that in the plant scale. The lead constant and exponents can vary. Information is not available at the present time for the correlation. You want to seek nimbleness in the equipment. The equipment should be flexible. As a result, you should always have a variable speed drive to cover problems that can arise. Variable speed drives have become inexpensive and add to the nimbleness and flexibility of the process. When I first started teaching this material, one of my participants really took me to task when I said to get a variable speed drive. He was very angry at me because, variable speed drives during that time frame was very expensive. And I don't know if they're expensive or not, but they let you cover yourself, right? To cover problems that arise, variable speed drives have become inexpensive and add nimbleness and flexibility to the process. I would always encourage variable speed drives. Now, correlations above is often seen in heat transfer textbooks. What's left out of heat transfer in agitated pot is this D over T ratio. This would be probably an important starting point. The D over T ratio is the ratio of the impeller to the tank diameter, right? D over T ratio is an important, very important ratio and should not be overlooked. Okay. D over T ratio can be changed and used to advantage. General method allows for changes in geometry on scale up. Okay. Anyway, I'm going to see if I can get my technician to stop this first for a while, and maybe we can restart a little bit later here. Anyway, let's take a break,